All right, hey everyone, welcome to the video. If you have been following right along in the class, what we're doing in section 3.1 is very similar to what we had done back in chapter 1. But I wanted to get a video out there that just has at least one example of the types of problems you might see that deal with transformations. Here in chapter 3, we're talking transformations of quadratics. So let's dive in. Part 1, question number 5 here is my example. It's actually from the chapter 3 section 1 review, but it's the type of problem where you just take a look at a transformed function and decide what the transformations are. We're not asking you to graph in this case. We'll do that one in the next problem. But what should you be doing? What I do when I see these is I obviously do identify the parent function. And the parent function here, you can call it p of x if you want, or it actually outlines it right there, is x squared. So the parentheses, the x, and the square are the parts of the parent function. And then the other numbers that are in the expression all do something. Okay, and I say all the other numbers. Also, the negative sign on the 3 is going to represent its own transformation. So the first thing I do is identify what are the things that are different. So we have a 1/2 out here being multiplied. We've got a negative inside here, a 3 being multiplied, and we've got a +5 at the end. Okay, and there is an order that we do them. We'll see that in the graphing problem, but I just try to decide what's happening in order from left to right so I don't miss any. So the 1/2, what's that guy doing? That is 1/2 being multiplied outside the parentheses or outside the original parent function. So multiplied means it's a stretch. Outside means it's a vertical stretch or compression. And since 1/2 is smaller than 1, it's actually not a stretch, it's a compression. And what that means is that all of the y coordinates would end up getting multiplied by 1/2. Okay, in purple we had that negative. The negative is inside the function, so I know it's a horizontal change. And negatives make reflections. So this is going to be a reflection across the y-axis. And remember, I know the y-axis runs vertically, but if we reflect points across it, it's actually a horizontal reflection. Okay, the 3. 3 is also being multiplied. This time it's inside the parentheses or inside the function. So we do have a horizontal change. But remember, with the horizontal stretches and shifts, we don't use the number that we see. For stretches, we use the reciprocal. And if it was a shift, we would use its opposite. So for stretches, if it's a 3 pictured in the function, it's actually representing a compression by 1/3. So compression by 1/3. And the only number else I have is this +5 at the end. Remember, when we add or subtract, that's a shift. Since the +5 is outside of the parentheses or outside of the function, it's going to be a vertical shift. So we can say that this shifts up by 5. Okay, plus is the positive direction, and since it's outside, I'm taking it exactly as it is. If that was a +5 inside, it would actually be moving to the left. And we will need that as we take a look at part 2, which involves actually putting a graph together of these points. Now, we had learned 2 different methods for graphing. I think I'm going to try to stick with this PRST version. It does allow us to do all of our translations last, or our shifts last. But that does require us to do one little bit of work right at the beginning. If we ever have anything other than just plain old x here, like I have a negative x, I have to factor out that thing. So I'm going to leave the 4 alone. I have a parentheses squared plus 5. And then with this little bit on the inside, I'm going to factor out a negative. And it'll leave me with an x minus 1. Remember, this step allows us to push all those shifts, or specifically the horizontal shift, to the last step. So what's actually going on here? Well, I've got a 4. That's going to be a vertical stretch by 4. It's outside and it's being multiplied. I have this negative. That's a reflection across the y-axis. Now this plus 1, or I'm sorry, this minus 1 that used to be a plus 1 tells us that we're going to shift to the right. Remember, horizontal changes like this horizontal shift, we're not going to use the number as pictured. We're either going to use its reciprocal or its opposite. In this case, I'm thinking plus 1 direction, which would be a shift right by 1. And then another plus 5 on the end. That's going to be a shift up by 5. Now, when it comes to quadratics, there are a handful of points that we should probably just know to start with. So the vertex of the parent function, remember this is just f of x, or maybe I'll call it p of x because we already have an f, is x squared. We know the vertex is at 0, 0, and we can literally just pick any points we want, but 1, 2, 3, and 4, and -1, -2, -3, and -4 seem to be the ones where the most interesting stuff happens. If you forgot about it, you could start with 5. You know that to get the corresponding y points, we're just going to square those values. So 1 squared is 1, and 2 squared is 4, and 3 squared is 9, and 16. And likewise, when we square the negatives, we actually get a positive, but the same value. So -2 times -2 is positive 4, and -3 squared is 9, -4 squared is 16. And what we're going to do is identify what we need to do to the coordinates based on the transformations we already wrote out. So if the r in PRST, the second column, stands for reflection, we're going to reflect across the y-axis. Remember, that's a horizontal change. I'm going to multiply all the x coordinates by -1. So I'm taking my -4, -3, -2, -1, and now I'm going to multiply them by -1. They'll all be opposite. Since there is no reflection across the x-axis, nothing needs to change about the y-coordinates. So you kind of have two options. You can recopy all of those values so that you have matching points. Or you can only change the coordinates that need to be changed. It's entirely up to you. I think I'll copy them just to help myself track the numbers better. Okay, so now we took care of the reflection. We'll move on to S, which is stretches and compressions. The only one we have is a vertical stretch by 4. Vertical means it's impacting the y coordinates. And that means we need to take all the y's and multiply them by 4. So I'm going to take my 16, multiply by 4. That's 64. That's going to be off the graph. I will move down to 9. 9 times 4 is 36. 4 times 4 is 16. 1 times 4 is 4. 0 times 4 is 0. And then we actually have the same set of values here, just increasing rather than decreasing. So to fill in that bit, 1 times 4, 4 times 4, 9 times 4, and 16 times 4. Okay. And like I said, nothing changed about the x's, so I'll recopy the green 4, 3, 2, 1, 0, -1, -2, -3, and -4. And then we actually have two shifts or two transformations. We have a shift right by 1. So that means I'm going to take all the x points and add 1. And we have a shift up by 5. So I'm going to add 5 to all the y's. So I will start with the most recent x values that we have and add 1 to them. So 4 is going to become 5. 3 is going to become 4. 2 is going to become 3. And you see what's happening here. 1 becomes 2. 1, 0, 1, 2, and 3. And then I'll take, to fill in this last column, I'm going to take my orange values, my most recent y's, and add 5 to them. 64 plus 5 becomes 69. 36 plus 5 becomes 41. 16 plus 5 is 21. And you can continue the column all the way down. All right, now that I have those values, since the instructions, actually, they don't say to graph the parent function, but I will just to make sure that we understand what's going on. So first, if I plot these points at 0, 0, 1, 1, 4, 2, 4, 3, 5, 6, 7, 8, 9, I can probably get just about those values. I don't think I could put the 16 on here easily. This is what my parent function is going to look like, which we should kind of all know and love at this point. And then I suppose in red, now I'm going to plot the points in this column, the ones that have been fully transformed. Everything's all done. There's no more like work to do other than plot. Well, 569 is going to be way too tall. It's going to be way off the graph. I think the first one that I can probably plot is 2, 9. So 2 and 9 is right here. 1 is paired with 5. I think I messed up a little bit here. These should be negative values, which makes a little bit more sense. Okay, negative 1 is paired with 21. No, what am I missing? 0 is paired with 9 again. Okay, so what I learned about this is that my original vertex, which was transformed not at all until the very last step, is now at 1, 5. That's this guy right here. Okay, so my original vertex got moved to right here, but in the stretches and the reflection and stuff like that, we ended up with a very, very narrow graph like this. And in some better problems, sometimes you get extra points, you get more points along the way. But for the purposes of this problem, that's all we got. And that'll do. That gives us a decent idea of what the new graph would look like. All right, and then for the last example in this video, this is one where we have an already this is not a parent function. F of x in this example is not what anyone would consider a parent function. This is just a generic function. It does happen to be a quadratic, but we're going to apply additional transformations to it. And for some reason, the x didn't transfer over for me, so this one should read 2x squared plus 6x. But when we do these transformations, we do them in the order that they are written. They actually have this word followed by to let you know that no matter what, even though translations are normally last in PRST, we're going to do them in the order that they are written in the problem. So first we're going to have a translation 6 units down, and then we're going to have a reflection in the x-axis, and then we are going to have a translation 2 units left. Okay? And they do say that the answer should be G. I'm not going to get too hung up on what the actual letter is, but if that's the case, I'm not going to use G until I do that last transformation in pink. But the first one, a translation 6 units down, let's call that G8. Let's call it H. of x is going to be whatever f of x is and 6 units down. Okay, just like we did in the first couple of problems, we're using this idea that horizontal things are inside the function or inside the f, inside the parentheses that make up the f of x, and vertical ones are outside. And also that translations are addition and subtraction, stretches and compressions are multiplication, reflections are negation. So if I follow this, all I need to do is replace wherever I have an f of x with the actual function. Okay, so f of x becomes the 2x squared plus 6x that was given to us, and then it just has a minus 6 tacked onto it. And sometimes it's that simple, like none of these terms combine. First transformation is done. Now in the second one, the reflection in the x-axis, I'm going to call this function j of x. We're going to use our previous function h. In fact, I'll stick with the same color scheme. And since it's a reflection in the x-axis, that's a vertical change. I need to negate the entire function. So what I do whenever there is a negation or a vertical stretch, you really want to make sure that you make all of the terms opposite, and you'll need the parentheses. So there's my negation, and here 2x squared plus 6x minus 6 is the function h verbatim. So I'll write it out. I'm negating the whole function, which is why the parentheses are there. And then I'll kind of distribute that minus. So j is going to be negative 2x squared minus 6x plus 6. And now, as promised, since this is our last transformation in pink, I'm going to make that one g of x. And what it's going to be is my previous function j, but since we're moving 2 units left, it's a horizontal transformation. It goes inside the parentheses with the x, and we're adding 2. Okay, left direction is normally negative, but we use the opposite when we do horizontal transformations. So this time, what I need to do is kind of copy j. So I'm going to be copying this line here. But whenever I get to an x, I need to replace that x with x plus 2. So what I do, and I strongly recommend you do as well, is I write the function out, and whenever I get to an x like I am right now, I'm negative 2 should be x squared, I just put a parenthesis squared. So it looks like negative 2 stuff squared minus 6 times stuff, okay, minus 6x becomes minus 6 parentheses, and then plus 6. And now that I've written that whole thing out, I'm going to replace those x's in the parentheses with just an x plus 2. And at this point, all we have to do is a little bit of algebra. So I will first, how about this? This guy right here should be x plus 2 times x plus 2. And if I multiply it, I get x squared plus 2x plus 2x plus 4, or x squared plus 4x plus 4. So it'll be negative 2 times that. Now I have to distribute the negative 6, negative 6x minus 12, and then there's just a plus 6 hanging out there. All right, still got to distribute the negative 2. There's a minus 6x. And you know what? If I put these two guys together, I'm going to get a negative 6. And one more step. Buy a little bit of room here. I'll combine my like terms. Negative 2x squared. How about negative 8 and negative 6x make negative 14x? And then negative 8 and negative 6, again, make negative 14. So, as a final answer to this problem, g of x is negative 2x squared minus 14x, just copying from that last line, minus 14. And that is what happens when you transform the function f of x given using a translation 6 unit down, and then a reflection in the x-axis, and then a translation 2 units left.